Woohoo! Thanks a lot. Maybe can I have your yeah, no. I've never touched a running system. Okay? So I think I have to present from here, which is not a problem. But the guy with the mic, maybe we should put the mic. My name is Romeo. I work for IBM in the IBM Cloud unit. And we have a cloud. So IBM has a cloud. That's one fact which a lot of people don't know. And we are, depending on the measure, always on the top three. Either one, first, second, or third, with Amazon and Microsoft. Here are the prices. You can check out this later. That's just to give you an idea where we are. So today I won't cover infrastructure clouds. It's plain virtual machines, or in the case of IBM we have bare metal machines, which are quite fast. But today I want to cover platform services. So that means everything is pre-installed for you and basically up and running in less than 10 seconds. Is it Apache Spark or a container having the Play framework inside? Who of you is a Scala developer? Okay, so 30% at least. So that means in the platform cloud, you only bring your data and your program code. All the rest is handled by the cloud provider. So maintenance, security, updates, backup, and so on. The IBM Cloud is based on OpenStack, Docker, and Cloud Foundry. And we call this Cloud Bluemix. And here are some examples of runtimes which you can use. The cool thing is it's based on Cloud Foundry, so the runtimes are plugins, and the plugins are hosted on GitHub. So there are more than 40 plugins for every programming language and framework, including Scala, and the Play framework runs in there, Akka, all that stuff runs, but also exotic programming language, even Go. Is that exotic? No, it's not exotic anymore. All that stuff is implemented in Go. Here are some examples of services, and actually that's an iframe showing the catalog of the services which are available. And there are more than 100 services in each and every category. So I just will walk you through them a bit. And what we cover today is Apache Spark as one service, and Swift Object Store as the other one. So the Swift Object Store, for those who don't know, it's elastic block storage. It's not a block storage, it's object storage, just to put files there. And the thing is, you just put files. You don't care about partitioning hard drives, backup, and so on. You put 1 megabyte there, or you put 1 terabyte there, or 100 terabytes. You are just charged per gigabyte. For those who know Amazon, Amazon S3, it's the proprietary one from Amazon, and there's OpenStack Swift, which is the open standard, open source version of it, kind of. So those two services we will use today in the demonstration. There are some DevOps services which might be interesting, and basically this resembles at the end in such an architecture which we have kind of seen in the previous talk. So you enter here in the cloud, you enter on a load balancer. The load balancer in the IBM Cloud is the the Cloud Foundry Go router. So it's written in Go. It's a HTTP level router, and it has a connector to an auto-scaling component, and your application is running in a container. The containers are stateless. They don't persist data to the file system, and therefore they are scalable. So the auto-scaling component will measure response time and throughput and also resource consumption on the containers, and then increase or decrease the number of container instances on the runtime side. Since we don't have persistent state in the container, we have to use a service for the persistent state, for example, a MongoDB, a CouchDB, or a SQL database. Some of these are also scalable. So if you're using a scalable data store, then you have an end-to-end scalable application. In this case, we are using the object store and a Spark service. All that stuff is available for free. We have a free tier, which is quite generous. So up to 50 GB of Apache Spark or Swift object store data, and a 4-core executor to play around with. Or you can even use it in production because it has the same SLAs as if you were a paying customer. And we have a program for startups. So are there any startups in here? Not too many. So then I will just do this in 1 minute. If you are a startup, we have a really cool program, up to $120,000 of cloud credits, and we also give you access to the IBM experts, to the worldwide expert team. I'm one of them, but we have a lot of more. We have more than 400,000 employees, and some of them are technical experts, so you get access to them. And we take you to new clients, and we take you to conferences, and so on. And I wanted to show you one example of such a startup. There's Chris. Yes, Chris. And he's an expert in the Go language and on Rocket, which is kind of the successor of Docker. And we just talked today about the startup program, and maybe we will get together in future. So now enough slides. Enough slides? Yeah, enough slides. And let's go to the demonstration. So in case you want to do this yourself, that's the link, ibm.bic/join IBM Cloud. And then you end up in the 1 month free trial, and then you will automatically get into the free tier.
Free tier is for 1 year, or?
Free tier is forever. And it has more or less this resources which you see here that you can use. So we have actually clients which are not clients because they're not paying, but they are running in production in the future, and they're quite happy with that. And the thing is, once you do something very innovative and you get a lot of additional clients, you need more resources. It's just automatic. It scales up, and then you have to pay for the additional resources. When you don't need them anymore, it scales down, and then you're not charged anymore. Okay, so that's Bluemix. I go to the dashboard, and there is no time to show you everything which is in there, so I just want to show you how to create such a Spark service to play around with. There are different pillars, so these are the application, Cloud Foundry application components. Here's a Docker cloud, so you can run Docker images here. You can run OpenStack virtual machines here. You have this list of more than 100 services, and then you have here the data science part, or the cloud-based data science services, which incorporate Spark, but also other databases like MongoDB, CouchDB, and the parallel version of IBM DB2, and so on. So what you can do here is you say a new service, and then you choose Spark, and then you name it. Let's say Zalando, and create. And then if everything works fine, in less than 5 seconds you have a Spark cluster up and running for your usage. Anybody can do this faster than 5 seconds? So now we have the compute engine. Of course, we need a data storage. So what I do here, currently we support only OpenStack Swift object storage, but there are more to come. For example, HDFS from Hadoop and that brings you data locality. So if you have I/O intensive work, if you're using HDFS, this brings the CPU and the hard drive together. Therefore, it will be much faster. So I will create such a Swift service.
One second. Like,
Yeah.
Is it for only new startups or existing startups? Like people in startups?
Up to 5 years. Up to 5 years and less than 1 million of revenue. Oh, it takes more than 10 seconds to create this Swift container. But it doesn't matter. I have prepared everything already, but we can go back later to this screen. Still running. Okay, it's done. So then you click on this. You can use the web interface, which IBM provides, but of course you can, since it's open source, open standard, you can use all the tooling around it, the command line tools, the REST API endpoints, the REST API stubs to write your programs against it. Here it says it's running in Dallas. We have more than 50 data centers around the world. You can choose. The next one is Frankfurt. There's Paris, Milano, London, and so on. And then you can just upload a file from 1 kilobyte to 1 terabyte. Using the web interface, it's limited to 2 GB. I won't do this at Zalando, of course. And then you can simply upload a file. So I've prepared a demonstration for you. Already instantiated the Spark service, the object storage. Maybe I take a seat because I want to type Scala code now. This is work with data. And then I click on the Spark service. So we use open source Spark, we use open source Swift, and we use open source Jupyter notebooks. Who of you knows what Jupyter notebooks are? Okay, minor fraction. So this is a web application. And this web application is able or capable of combining text, which is written in Markdown syntax. Who of you knows Markdown syntax? Okay, good. The others have to use Google and just Google for Markdown syntax. It's a very cool way of writing text and have it formatted really nice. So I don't use Markdown syntax here. This is, oh, by the way, I have to show you how to create that. So I go back to the Spark service, which I have created right now. And then you say new notebook. And then you say stuff or whatever. And then you have to choose between Python and Scala. And I tell you why this is the case. So let's do that. So Scala and create notebook. And then you can use it. Okay, then you are at the point where I am here. And so the Jupyter notebook works in the following way. It's a web application and it's capable of interacting with interactive programming languages. And Scala by itself is not interactive, but there is an iScala kernel. And the iScala kernel actually allows us to use Scala as an interactive language. The same holds for Python and also for R. And a lot of other interactive languages are supported in this Jupyter notebook. So you can basically type your code here, you can execute it on the cluster, and you will see the result immediately. Let it be strings returned by the execution, or you can even plot charts using Python framework, and you will see the charts there. So you can mix code, locations to data, and documentation in one single application. That's the basic idea.
That's a kind of worksheet for the cluster.
Exactly, yeah. So the initial idea of that stuff was done by Mathematica. It's a math program. That's the basic idea. There's another Apache project which does the same. more or less the same. This is called Zeppelin. Thanks a lot. I tried to find out what is the difference, and the main difference is it's Apache. So it has an Apache license. So they basically built the same stuff again. So we use Jupyter because it's much more mature. It's much older. So I will now do, depending on the time we have, two analyses. One is proteomics. So I want to do some protein analytics. So that's bioinformatics. Just to give you an idea what proteins are. In your body, or your body is built of cells. In these cells there is a kernel. In this kernel there is DNA. And DNA is a character sequence of 4 letters. So it's not like a PC working with 0 and 1. It's a bio-PC working with A, C, G, and T as letters. And this DNA is red. And it's not an 8-bit system. It's like a 3-bit system. It always takes 3 of these letters. Let's get this picture here. So it takes G, C, and U, for example, and then this means the machinery in your cell takes one of these amino acids, which are here, which is another component, and these are assembled. And if you assemble a chain of amino acids, then the following happens. The amino acids are molecules. They are assembled. They are between, let's say, 50 and 1,000 characters long, or elements long. And then what happens, this molecule is not a straight line, it folds. It will fold into a very deterministic 3D structure. And that 3D structure actually defines the biological function of that protein. Examples for proteins are, for example, enzymes. Enzymes are catalysts for chemical reactions, which are in your complete body. It's the central thing to regulate life. So enzymes regulate all chemical reactions in your body. And by reading genes and creating proteins like enzymes, it up and down regulates functions in your body. That's basically how cells work. Another type of a protein is, for example, a hormone. And hormones are nothing else than asynchronous messaging between cells. So synchronous messaging in your body happens through nerves, and asynchronous messaging happens through hormones. So if one tissue wants to tell something to another tissue, it just creates hormones in the bloodstream, and then the messages are read by another cell. So, having said that, I want to show you what I've done. And actually, I have done this yesterday evening in 3 hours. So it's really fast using Spark. There are protein databases in the internet where you can download protein sequences of organisms. One is UniProt, for example. And here you can search for organisms. Let's say human. And then you get all the known proteins which are in humans. And then you can click on one. And somewhere you can download the sequence file. I don't know where this is. But just to give you an idea how this looks like, such a sequence file. Oh, it's too big. So it's 30 megabytes. So these are all the known proteins of humans. And let's go to a terminal and have a look at this sequence file. Where's that folder? And then we just one, two, three, four. Okay. So what you see here, that's one line. And you, I broke it up. Huh? Poor guys in the last row. So this one is just meta information. That's the species, human, and the name of the protein. And there, that's the amino acid sequence. So these are the 42 or something different amino acids which we are using. There are more on the planet, but we are only using 42. And this protein is assembled in the cell, and this chain falls to a 3D structure and does a certain biological function. So what I just wanted to do is I wanted to detect the species based on the distribution of amino acid structures. So I have downloaded 2 proteomes. Proteomes means all the proteins of one organism. One is a human and one is a wheat. Did you know that wheat has 4 times more genes than humans? Yeah, more evolved, maybe. So, and I want to just feature extract. That's what data scientists do in the first stage of a data processing pipeline. They feature extract from their raw data, and I just want to do some feature extraction. And now I'm back in Bluemix in my Spark service, and I will just do the following. Who of you has experience with Spark? Okay, around half. So I have to increase size, of course, here. Oh, that was too much. Okay. I will scroll up, no worries. So, in Jupyter, you can just type in your code and you hit run. What I'm doing here is I'm accessing 2 files, the 2 proteome files in that format, and create a so-called RDD. So for those who have no experience with Spark, RDD is a proxy object for data lying on a cluster. It can be Amazon S3, it can be OpenStack Swift, it can be FTP, it can be a file on your hard drive, it can be HDFS from Hadoop, that doesn't matter. It's transparent to you. It takes care about caching, it takes care about in-memory processing, but on the RDD there are methods. And the cool thing is, if you're using the methods on the RDD, your program automatically is scalable and parallelizable. So it doesn't matter if you run it on 1 or 100 or 1,000 nodes, you don't have to change the program. That's a really cool feature. So I'm reading these 2 files and I cache them. So I tell the Spark executor to cache them in main memory. What I do later is I will generate 2 functions. One function is a function to generate k-meres. K-meres are subsequences. So I take the whole amino acid string and I create subsequences of length k. And I create all possible subsequences of length k, preserving order. That's this function here. And the second one is, I will walk you through a bit here.
Is it like n-grams or something?
Exactly. And here is the RDD, which contains all the proteins from one organism. I filter out this meta line. So this is functional programming. Who of you is capable of doing functional programming? Maybe all the Spark users. So I apply a function which actually returns true or false if the string contains this ejector here, in order to filter out the meta information. So after that, I have only the protein sequences. Then I use the map function. That means I apply the k-mere extractor to each line. Okay, and what it returns a list of the k-meres. And I flatten this out because I don't want to have the list. I just want a flat list of k-meres. And then what I do, I count them. Okay. And then what I do is I normalize them by using, so I'm counting the frequency of each k-mere, and then I take the max and create a normalizing constant, and then I can apply this normalizing constant to each and every k-mere. So I get the frequency of each k-mere, and that gives me some sort of measurement or spectrum of k-meres per species. So I could repeat that for different species. So I will now run this, then you might get the point a bit better. K-mere. Well, let's do it step by step. So this will take some time. I can't because my account doesn't allow. Yeah, but you have to provide a credit card. If you give me one, I can show you. Okay, so this one has 4 workers, so 4 threads, and most likely on one single Docker container in this case. Yeah, it's still running. So this star means that it's running, and eventually you get back your results. So this happened now. The result is now stored in the read profile, and I can now tell the service get me the first 10 rows, and then these are, oh, I should have printed them, of course. So I'm not, so Scala print array. You have to use some functional programming to do that. I just forgot how to do this. So yeah, it will give me, I think it will just give me the memory address. We can try. With me? To list, okay, and then just print that. Okay. No? Okay. No, actually you can use functional programming. You can actually pass the print line function to each element, but I forgot the function to map. I said map? Okay. Yeah.
For each.
Okay, let's try map and then try for each. So that would be the functional programming style. Not too bad. It doesn't give a compile error. Yay! Okay. So who didn't understand this code? Hands up. Okay. So functional programming means, in contrast to like iterative programming, is in like plain Java, you have a list or a collection, and you iterate over it, and then you apply a function in the body of the iterator. In functional programming, you turn it. You say map, for example, and you apply the function to each element, but this is done by the programming language. And I just passed print line. Maybe later, for sake of time. So what I've done here is, these are the 3 meres, so the k-mers with k equals 3. And that's the number of the relative frequency. So you see in wheat, the sequence of 3 A's of the amino acid A, which is orosin or something. Let's go. What is A? Okay. There's my tab. There's my tab. Here's my tab. So I do this. So let's take it for 100, and then you see that the frequency decreases because I've sorted this. I've sorted this here, and that means for wheat you get a certain spectra or profile, which gives you the list of freemiers and their relative frequency. And this is different for each species. And that's how this works, okay? So what I then do is I query my profile with one single protein without knowing if it's human or wheat, and then I compare it. That's that I'm doing this here somewhere. So I will let this code run, and while it runs I will explain it to you. So I'm doing the same for humans. So that one is the wheat one. Yes, of course. Sorry. So I'm doing the same for humans. So I'm getting the spectra for humans, and then I take the first protein of the human proteome and do the same thing. I get the spectra of this one protein. That's this one here. So I can say same stuff which I've done here. Take 100 and print line. Oh, we know how this works, fortunately. And you see here, that's the spectra. And now what I'm doing is I join these two collections. Again, this collection is a RDD. The RDD is a distributed data set. It can contain 1 megabyte, it can contain 1 petabyte, it doesn't matter. That depends on your resources. And I can now do joins on terabyte data if I like. And I join these two on the k-mer as a key. So I get, for example, the AFH k-mer of the proteome of wheat or humans, and I get the AFH freemier of the query protein. And the join operation returns me the key and the two values. That's actually what happens here. I will show you this. Print line, join, then take the first result of this and run it. Let's let this run. And it gives you as a key the k-mer and as a value a tuple. That was not successful. I have to do the same array stuff again. That print line. Then of course I can also take 10. Thanks. So you see here, the join operation returns me the key and the two values. That's quite handy because now I can use the two values and I can create a score. So the more different they are, the more different the proteins are from each other. So I subtract the two values, and to get a score I take the absolute value. And I do this for each k-mer, and at the end I sum it up. And after that I get a score, and if I compare the human protein against the human proteome, I get a score of 108, and wheat against the human query protein, I get a score of 118. And since the bigger the number is, the more different they are, I see that the human is more similar. So why am I doing this in the cloud? Because that I can do on my laptop. The cool thing is, if you have enough or nearly unlimited resources, you can do parameter space exploration. Because who knows if I've taken 3 as a k-meter size. I don't know if that is the optimal one. It can be 1, 2, 3, 4, 5 or whatever. And the cool thing is I can just do a parameter space exploration. I don't know grid search, so we have to discuss this later. There's my... okay, so let's take this one. I let it run and then explain it to you. And so what I do here is I'm defining array. So for the k1, 2, 3, 4, 5. And I have a for loop from 1 to 5. And the only parameter which I change is k. So the k-meter size of 1, 2, 3, 4, 5. And all that stuff which I've done now, I'm doing here in a loop. And what this will do is it will print me the difference between the human read score and the human score. And the bigger the difference, the better, the more optimal the value for k. So I see here with 1, the difference is only 0.01. Oh, sorry for that. I have to scroll up. I know. It's only 0.01. With 2, it's 0.5. And this way, I will find the optimal value for k. Only for the dataset, of course, which is 3, by the way. With 5, you even get a negative 1. So, and the thing is, you can do that not only in such an analysis. So, of course, if you're doing proteomics, you're using much more advanced algorithms. So that was just a way to show you a very basic analysis. You can do this actually with much more advanced and complicated things. And that's the last thing I want to show you. Then I'm finished. So that's for actual use case, which I'm currently doing for a Swiss hospital. So they have cancer patients and they are doing CT and PET imaging. What they deliver to me, they are feature extracting from these images and some other patient data features, around 100, and give them to me. And who of you is knows about machine learning, supervised learning? Also half. So the basic idea is I have to predict the outcome of the treatment and the event of death. So based on the images, based on the treatment and some other features, I have to tell if this patient will die or not. It's my job.
You tell the patient?
I don't tell the patient, I tell the doctor. So what I do is I'm using MLlib. MLlib is the machine learning library for Apache Spark. And there are different algorithms. If you are in machine learning, that's totally clear to you. It is called random forest, which is a classifier. And it's used here. The thing is, I have a huge number of parameters which I can pass to this random forest classifier. And I don't know which combination is the best one. Therefore, I do a parameter space exploration. So I take arrays of possible values for each parameter. And of course, this is a complex process because if you multiply them, you get a huge number of parameters to test. But the thing is, you can assess the quality of each prediction based on the set of parameters, which I'm doing here. So I'm getting the error. And I store each parameter vector plus the error. And I let it run. I let it run on the cloud. So I can close down my laptop and get some sleep. Because it's really loud if it does that.
Is it continuous function of these parameters or?
It's a binary function. It's death or not death.
No, but this search, like test error
Yeah.
as a function of these parameters.
Yes, it's a value. It's a value between 1 and 0, which gives you the percentage of error. Then what I do is I have this parameter list and the errors. I sort by the lowest error and I sort by the less complex model, which is the second parameter, and I take the head, so the first entry. So I have the optimal parameters. I use them to train the classifier again. And for those who are in machine learning, you do have to again test the accuracy of the final obtained model, because if you are doing such a parameter space exploration, you are fitting the parameters to your data. So they are perfect for your data, but if you get new data, you might end up in a bad result. Therefore, before I do the analysis, I take some data apart, which is 20%, and then I reassess the accuracy. And at the end, I get the final performance of my model. Okay. I will just let that run. It takes a couple of hours, but I just start this here. So no, I get the already feature extracted data. The cool thing is the software of the CT and PT scanner, they already does that for us. Oh, it's nothing. It's like 100 to a matrix of 100 to 100.
Images?
The data set images, that's a big data set, but my data is very small. And the problem is I have used logistic regression. I got really bad results. Then I switched to random forest, and that, yeah. It's 100, it's a matrix of 100 by 100, so it's 100 KB or something. Yeah. It still needs the cloud for compute, not for data storage. So let me just finish this, or let's just copy paste this, and I have just to access the file in the object storage instead of my local file system. So that means I only have to change this one to this one, and then it's done. You can do that as well. You also get the Spark endpoint, so you can have a local driver and connect to the Spark server in the cloud. You can also use the REST API and have a web application connecting to it. That's your choice. So I let this run. I hope I haven't done something wrong. So I should see a star here. That means it runs. And then I should see eventually data appearing here. And that data which will appear here later is the test error and the model parameters which I've just tested. And this will just run for a couple of hours. And after that, I will have the optimal model. So I'm finished. And I'm open for, let's say, 1 or 2 questions, and then...
How do you do real-time update of like new data coming or something? Is it possible, like a real-time update of your model or something like that?
Real-time update of the model?
Yeah.
You have to rerun. You have to rerun.
Rerun?
Yeah.
You can't update it, like...
The model itself, no. That's the limitation of Spark. Okay. So you see here, that's the output. So the first one is the error, and the second... and the rest of the numbers are the model parameters. And you see here it's different accuracy, and then after the process has stopped, I will get the optimal parameter set. Okay, maybe one. Oh, so many questions. Okay, yeah.
And if you saw that you're using Spark 1.4, how frequent is the version updated or get updated?
I don't know, because this service is running since October. And I know that there's version 1.6 with the R integration, but that's on the roadmap. I can't tell you. Okay, yeah. It doesn't fit here, because the only thing which is provided by Cloud Foundry is the web application of the IPython notebook, which is automatically generated for you. But if you want to have a REST endpoint or a web application to your data, you can use Cloud Foundry to have your runtime installed there. You can train it, you can store the model parameters into a file, and you can reload it from the file. So you can recreate this model object. Yes, so to give you the idea, what you are getting back from the training here is a model. So you say random forest string classifier, that's a model object, you can persist the model object and reload it. And then you can use it for online prediction. So the last question, then I really have to give stage to the next speaker.
I think it's the Google service is called Google Prediction Engine. So you upload your features, it applies different algorithms for you, and trains the best model for you, and then you can ask questions. So you can have both things.
Yeah, so my opinion, the main difference between the Google service and also the Microsoft machine learning service is that this one is open source, open standard, no vendor login. You can put it to any data center. In contrast to Google and Microsoft, exactly. That's the main difference. Okay, so I think I have to really quit then because there's another talk. But I'm here, so if you have questions, please contact me later. Okay.